All right. So let's talk about the specifics of the gamma camera performance for this kind of imaging. So we know that something that's really important when we're talking about gamma cameras is the energy resolution. And here we're just talking about what are the energy of photons that are being picked up by the gamma camera. So we're talking about the pulse height analyzer system. And if you want to learn more about this, you can refer to the previous webinar on the subject. But for this type of imaging, it's sufficient to have an energy resolution of 10%. The energy resolution is based on this thing that you're seeing on the left-hand side. So the energy of photons that are picked up by the camera have a certain distribution, which is similar to what you're seeing in that graph I've hand drawn over there. So an important structure on this type of imaging is the pulse peak, which is that structure that looks like a mountain. And we have to decide how much, so we'll look at the center of that peak and we'll see how much information should we take from either side of the peak in order to get a good image. And that's the energy resolution. So for this type of imaging, 10% energy resolution at low energies such as 160 kilo electron volts is usually sufficient. So a low energy resolution is sufficient. And what the other things that we're looking at is rejecting the scatter. That's done by the pulse height analyzer circuit, throwing away these photons which we know are coming from scattering processes. And this will also improve the image contrast. So it's good to know how the energy resolution depends on the energy of the photons. So this is the way that it's related to each other. The intrinsic resolution is inversely proportional to the square root of the photon energy. So if you're not sure what that means, you just have to think about what will happen when the energy increases. So if the energy of the photons is increasing, what will happen is your square root, which is in the bottom, is increasing. So the number is actually getting smaller. So what that tells you is that the resolution of the image is decreasing as the energy of the photons is increasing. And is decreasing as the energy of the photons is increasing. And the reason for this is that the number of scintillation photons produced depends on E. And because it's a statistical process, the number of fluctuations produced is also dependent on the E. So we've talked about this in a lot of detail when we were talking about the gamma camera. So you can refer to those webinars on radionuclide imaging, but I won't go into too much detail of this right now. So some other important features for the gamma camera performance is since the camera is moving in multiple directions, you're getting multiple views of the same objects. So the detector must have the same response at all views. Otherwise, you'll get artifacts because the computer programs are working in such a way that they assume that the detectors are all looking at the object in the same way, but there's no difference in the detector response. So that's one important thing to know. Another thing is that since the camera orientation is actually changing, because the cameras are physically moving around the patient, in order to have the same response, the photo multiplier tubes within the cameras are fitted with metal shields. And what this does is, because of the way that the orientation of the cameras is changing, the orientation of the photo multiplier tube with respect to the Earth's magnetic field is also changing. And this can produce variations which will give you different responses depending on the orientation of the camera head. So that's not something that we want. And so in order to prevent that from happening, what we do is we fit the photo multiplier tube with a metal shield. And what this does is it prevents fluctuations due to variations in the Earth's magnetic field. Okay, it's also very important that the camera head is uniform. So the uniformity of the detectors in the camera head must be, the variation must be less than 3%. And you also need to apply quality control measures such as using sensitivity correction maps and energy and linearity corrections. And we'll go more in detail about these, not in today's session, but in later sessions. So we can take a chance to just look at this image on the left-hand side here, just to get like a picture of what is the setup. I'm sure many of you are familiar with the setup looks like already, but yeah, so we can see there where the CT component is located. We see that there's two detector heads. Those detector heads contain both the collimator, the scintillator, PMTs, and the associated electronics, and then the patient bed is in the middle of all that. And then there's the computer to which all this data is passed and which is acquiring the data. So yeah, that's what that looks like. Yeah, it's also important to make sure that the gamma camera performance is derived from a high count image. So we know that it's the count or the number of photons reaching the camera that determines the image quality. So you need a high count image. You need each pixel to be created by around 10,000 counts with a statistical error of 1%. So the way that you can check if this image is being correctly formed is that you can image a uniform flood source. So a uniform flood source looks like the image on the right-hand side there. The count is uniform in every point of the image and should give you like a uniform, single contrast thing like you're looking at on the screen there. However, if there's things like the, sensitivity of the detectors is not calibrated, etc., you'll, instead of getting a uniform image like the image on the right, you'll get an image that looks like the image on the left-hand side. So what you need to do is apply these corrections that I talked about earlier, and you need to do them regularly. And we'll look at how regularly those need to be done in just a little while. But yeah, so we want a high count image with around 10,000 counts per pixel. Another important thing when we're talking about the equipment used to derive the image here is how the camera head is rotating. So the image is formed by the rotation of the camera head. This is a very complicated motion, and the radiation which is being picked up has to be picked up in a very precise way. So it's absolutely crucial that the rotation of the camera head is done extremely precisely in such a way that the detectors are correctly positioned in order to get the right information and produce the correct image. So what do you need in order to prevent artifacts which are arising due to the camera head rotation? So you need the cameras to move accurately and also stably. And the mechanical alignment of the gantry and the camera heads is extremely crucial. So there's a really massive mechanical component which decides whether you're getting good images or not. The rotation must be perfectly circular, and the rotation has to happen around the rotational center. So the centers that we're talking about here is the center of rotation and also the center of data reconstruction. And so the really important thing when we're talking about the camera head rotation is that the rotation has to be perfectly circular around the mechanical center of rotation, which is also called the COR. Yeah. We also need the cameras to move at a constant rotation speed. And this is so that we get the same acquisition time for each projection angle. So just picture it as happening this way. If you just picture each photon that's being caught by the camera head as a tomato that's being thrown, if the camera is moving faster in some areas and it's moving slower in some areas, if in the areas in which it's moving slowly, it will be able to catch more of the tomatoes that are being thrown. But if it's moving very quickly in some areas, it will catch fewer tomatoes. This doesn't mean that those places in the body are throwing fewer tomatoes or emitting fewer photons. But however, because the rotation speed is different in different parts, we're catching few of the photons at certain areas, and so this will lead to artifacts being produced. So one very crucial thing is that the rotation speed should be extremely constant with very little variation, so that each projection angle gives a similar acquisition time. So what is a projection angle? Just picture like a line coming out of the camera head and moving through the center of the scanner. That is one projection angle. So the camera is like a human eye, which looks, along this line which is coming out of the camera. And at each position, that line collects all the photons along the line, and that's one projection. So yeah, that's what a projection angle is. Just picture a line coming from the camera head. So a few other important things relating to the camera head itself. The face of the camera should be parallel to the mechanical axis of rotation. And this is so that you minimize distortions in the reconstructed image. And you can see that there's two configurations which the camera head can have. These are called the L configuration and the H configuration. And in both of these configurations, all these previous things that we've talked about must be present. So yeah. So the H configuration, the camera describes a 360-degree arc. So 360 degrees means that the camera travels all the way around the circle and comes back to the original position. Or views are acquired along 360 degrees. This is used for general imaging. The L configuration instead describes a 180-degree arc, and that is used for cardiac imaging. So the L configuration is the one on the left. It looks like the alphabet L. And the H configuration is the one on the right, and it looks like the alphabet H. So we can see if you look at this picture here, these are both images acquired of the same sort of object. The image on the left-hand side is acquired using the H configuration. The image on the right-hand side is acquired using the L configuration. And I've taken this image from IAEA.org. So you can see in the 180-degree arc that those things which appear as blue circles on the left-hand side image have become smeared out across the object. So this is something that happens when you're using this L configuration. There's a certain area in which you get like a clear image, but there's also distortion in areas which are distant to the acquired projection. So that's just something to be aware of when you're thinking about these two types of configurations. That's why they're used for different types of applications, because you only can use them for certain clinical applications because of this type of distortion which comes up. Okay, so we've talked about the positioning of the camera head and the movement of the camera head. Now let's talk about the components within the camera. So, and I'm just going to take a sip of water. Okay, so one of the important components in the camera itself is the collimator. So the collimator design is related to the sensitivity of the camera as well as the resolution of the camera. And we know that there's always a trade-off between these things. So sensitivity of the camera is related to how many of the photons are being picked up. The resolution of the camera is related to how small are the structures that we're able to image. So what is the ideal collimator design for this type of imaging? You want parallel collimator holes. You want the hole and the septa size to be uniform across the detector field of view. So what does this mean? We know that the collimator consists of two things. The collimator consists of the holes within the collimator. It also consists of the material which is separating these holes from each other. That's called the septa. So both these aspects, the shape and the size of both the holes and the material between the holes changes the sensitivity and the resolution of the collimator. So what kind of hole and septa design do we need for SPECT? You need the holes to be as perfectly parallel as possible, highly uniform holes with very little, lack of uniformity between them, and we need this to be uniform across the field of view of the detector. What is the field of view of the detector? It's the active detector area that is picking up photons. So that's that. What is the best way to create this kind of collimator which has these functions? There's something which is known as a microcast collimator. What that means is the collimator is being cast in lead, and the outcome of this type of process of manufacturing is that you get a very uniform collimator. However, it's more expensive as well. So yeah. A few other things between when we're talking about the collimator design. There are pressure-sensitive safety devices which are included in the collimator design. And how this device works is if there's ever a point when the collimator comes in touch with the patient body, instantly the safety device feels a certain amount of pressure. There's an electronic circuit which is triggered, and the gantry motion is disabled instantly because, yeah, that's not supposed to happen. The reason it might happen is because we want the collimator to be as close to the patient as possible. So we are trying to have a type of camera head motion such that the patient detector distance is as tiny as possible, which is not such an easy thing because the human body is not uniform. So this extremely complicated equipment has to move very uniformly and stably, but it also has to move in an orbit which is as close to the contours of the patient's body as possible. So one of the features which makes this kind of movement possible is a pressure-sensitive safety device, which if the patient's body is touched by the collimator at any point, the electronics are triggered and then the gantry motion stops, the circular motion stops, and the examination is halted. So this is what I was talking about here. If the patient to detector distance is as small as possible, the image resolution is as high as possible because we're able to catch as many photons as possible. So if you're just having a normal elliptical or circular orbit around the patient, like the image on the top over there, you can see at some points, and this is like a view of the patient. Yeah, that's a stylized view of the patient, obviously. But you can see that at some points, the detector is very close to the patient's body. And then at some other points, the detector is extremely far from the patient's body. So what will happen is that the projections at those views will pick up like very few photons, and the overall image quality is going to be reduced. And the computer is also going to have a harder time stitching the projections together. So instead, we don't want this kind of, this would be the easiest way for the cameras to travel, because we also know that the cameras have to travel in a very uniform way. But in order to maximize the image resolution, instead we make the detectors travel in such a way that the orbit of the detectors is tracing the contours of the patient's body. And this is a technique which is known as body contouring, and you follow it in a few different ways. So you can make the cameras move in an elliptical orbit, which is as close to the patient's body as possible. What is an elliptical orbit? So we know what a circle looks like. An elliptical orbit is just a squashed circle, which lies as close to the patient's body as possible. So one way in which this body contouring takes place is that there are rows of infrared detection devices placed like right next to the collimator. So you'll have two rows of infrared devices. One is the inner row and one is the outer row. And the computer says that it's okay if the system says it's okay if the outer row is like beam is being interrupted by the patient's body. But as soon as the inner row beam is interrupted by the patient's body, that means the patient is too close to the collimator. And once again, the gantry rotation is shut off. So yeah, that's how body contouring works. So you use different types of systems. You use infrared detection devices. So there's a beam of infrared radiation. The computer is measuring that beam and seeing is it being cut off or not. And you have two rows. You also have these pressure-sensitive safety devices. So yeah. Yeah, and that's what we were just talking about just now. Only the outer row beam is interrupted by the patient outline. Another thing when we're talking about the equipment of imaging is the patient table itself. So the objectives for the patient table are it should be strong enough. Ultimately, the goal is to minimize patient movement, because patient movement will lead to artifacts appearing in the image, distortions, movement-related artifacts, etc. So what you need is a table which is as small as possible, so it's not taking up space within the scanner. And we'll discuss why in just a second. It needs to be strong enough to hold the patient's body without moving itself. It needs to keep the patient as comfortable as possible, because a patient who's comfortable will also move as little as possible. So the ultimate goal of patient table design is to have the patient be still. So it will be constructed of carbon fiber or similar material. It should be able to support 200 kilograms without sagging. Yeah, the table of the table itself should not move. So any type of sagging, etc., is not, a good thing. Should be of narrow width, so it's taking up as little space as possible in the patient table. So the patient table itself should not attenuate the gamma photons, because that will utterly defeat the purpose of what we're trying to do. Each of these gamma photons is really precious in capturing the image. So anything which comes between the patient and the detector and absorbs these photons is a bad thing. The patient table should definitely not be a source of attenuation. So we're looking at an attenuation of less than 10% if the gamma photons are at 140 kiloelectron volts. And we know it's important to discuss the energy, because we know that attenuation is different at different energies. So all these things are defined with certain standard ranges. The patient table should have restraint straps to prevent patient movement, and you should also have a narrower head restraint for brain imaging. So yeah, so we just got a few minutes left till the end of the session. So we'll just talk about some quality control measures before the session ends. So I don't know if you can see this very clearly here, but the image on the left-hand side has a circular ring artifact. So artifacts which come from this type of technique, because of the motion of the camera head, usually tend to be circular. They can be both hot or cold artifacts, which means they can either show up as bright spots on the image or as dark spots on the image. And the problem with these artifacts is that they're very small and they usually look very similar to real image features. So it's extremely hard to detect these artifacts. So the best way to prevent these artifacts is to have very stringent quality control measures and good algorithms, so that these artifacts are eliminated before they reach the image that the radiologist is looking at. So we also do things like calibration. We talked about the different types of mapping which we do in order to prevent artifacts. So you can see over here on the top row, these are images which are taken of a uniform flood source. Now, before the detectors are calibrated, you are seeing all kinds of features appearing in the image, although what you're imaging is actually a uniform source. Once the calibration has been done, you get an image that looks like the bottom row over here. So it's really important that the calibration is done according to the correct schedule and in the proper way. This is something that I've taken from iaea.org. So it's just giving a list of different types of quality control schedules that you can follow. So there's a whole bunch of different things that you have to look at when you're ensuring the quality control of the imaging equipment, and different places have different protocols. So these symbols like A plus W/M is just referring to different units of time, annually, yearly, etc., monthly. At time of acquisition, etc. That's A. So what are the different things that you need to be looking at when you're doing the quality control? You need to see, is the rotation happening around the center of rotation correctly? Is the pixel size being calibrated properly? Are the images which are being formed, you do your uniformity mapping to make sure with the flood source that you're getting like a uniform image. So you take the resolution in air and see, what kind of image are you getting? Does there have to be some recalibration? You recalibrate taking into account the scatter. So slice thickness, system volume sensitivity, detector to detector sensitivity, sensitivity/uniformity with rotation involved, head-to-head registration. So all of these are things which will affect the type of image that you're getting. And if these things are not maintained properly, you won't be getting an image which is useful for clinical purposes. So because the way that these things will go out of order depends on what is the equipment made of, like the mechanical motion itself. As we know, the mechanical motion, there's all kinds of things like friction, etc., which are going to throw the calibration off. The electronic system needs to be constantly calibrated to the equipment, etc. So if we are aware of how often these things go out of order, then we are able to draw up like a proper quality control plan. So we can say, okay, this is usually the time when, the camera heads stop rotating correctly around the center of rotation. So around this time, we should do this type of calibration check, etc. So these are some examples of the type of protocols that you can use for this type of imaging. And I got this from a PDF, which is related to quality control for SPCT imaging.